Hello, everybody. Let's say that you wanted to do a circuit. Way back when, you want to have some sort of circuit that a simple. Let's just do a simple. Whenever you flip the switch, something turns on. Let's say it's a motor turns on or an actuator, or, something like that. Let's say a switch turns on. So, what you would have done is you would have put a power supply in the system. Okay, and then we're going to have a wall here that's connected to negative, and we're going to have a wall over here that's connected to positive. So here's positive and negative. Okay, so this would be called, this over here, the actual name of this would be called, this would be a bus bar. And this is still a current thing where you have, one terminal come in. We did, I think in class, we did terminal blocks, which is a form of this, lots of places to connect other things to it, right? Same over here. We've got lots of places to connect. We bring in power one time. We can bring in DC power. We can bring in AC power, whatever. Okay, but we're just going to bring it over to a bus bar or terminal block so that we have a place to tap into it and make multiple circuits. So if you want to turn on a light bulb, in the past, I'm going to skip forward a page, okay? I'm going to make a new page. In the past, we had a lecture and I said, oh, let's make a flashlight. And so I drew it like this. I said, yeah, what do you need a flashlight? What are the key things you need to make a flashlight? Anybody remember this? You need three items to make a LED flashlight.
Battery.
Power. Yep. What else is in a flashlight?
A bulb.
Okay, a bulb. Okay, a bulb. So we want a load, and in a flashlight, that load is a light, and in our case, it could be an LED light. And there's also one other thing in that bulb that it's doing. That's the current limiter. That's the resistor.
Switch.
And then the last thing you need, you need a switch. Okay. Now you guys can all make that, right? You have all put batteries in a flashlight. You've all changed the bulb, and you've probably pushed the switch. And if I asked you to make the circuit for that, you would go, oh, I think it looks like, let's see. And we even talked about this. Let's put in the switch there, and then a normal flashlight would have basically a bulb, and that bulb would be also have, hold on a second, that bulb would also kind of have a resistor, a resistance to it. So this would be, this whole thing here, that would be the bulb. 5-volt battery, 3-volt battery, 1.5-volt battery, whatever you got switched, there's a flashlight, right? So then if you had an additional circuit, we could do an additional circuit on this as well. We could say, hey, let's do two things off of this. Let's put in another switch, and let's make an LED part of it. And so then you would say, all right, we need the LED that puts off light, and still you got to have the resistor. And I'll just bring it back all the way over here. Anything wrong with that circuit, say no. There's nothing wrong with that circuit. So volts DC. Remember that? Okay. So
there's two flashlights in one. That's what you did right there.
Yeah. Is that legal?
Yeah.
I think so, right? Is there anything, if the only thing that you got to worry about in something like this, you tend to take you tend to say, okay, is this okay? And then, is this okay? Is there current there and current there? The one thing you got to be careful of when you start putting circuits together is you have to start saying, oh, what could happen in this circuit? Is there anything going on right in here as you traverse and you come through here, instead of going back there, if you went this way, is this one okay? And so there's a little bit of resistive coupling you have to watch out for. But in general, this is fine. And in fact, if you were to go to your car, you would see that you have one battery in your car, right? One battery. And hundreds of circuits that run off of that one battery. So it's okay to run lots of things off of one power source. Make sense? Okay, so let's go back a page now. So back to our PLC drawing. So what I've done here is I've changed the screen around a little bit. Here now, instead of being on the left side, I put the power up on the top instead. And so now basically we're going to put inputs on this side and outputs over here. And if you go back and look at this for a minute, logic-wise, the switch is an input to the logic. The switch is saying from you, that's your human input that says, do I want to turn on the flashlight or not? That's your input. And what's the output, essentially, then, of the flashlight? It's the light, right?
Light.
Right. It's either heating up a filament or turning on an LED, depending on which kind you have, right? You're the input, there's the output. Okay, so back to PLCs. What we're going to do now is we're going to just make multiple logic circuits, because that's what we just did. We just did a logic circuit with the flashlight. We said something like, I guess if you were to write out the words for that logic circuit in the flashlight, you would say something like this. You would say, hold on. You would say, anytime, and then you guys are fairly comfortable with variables. So I'll say anytime, some input, X and or Y, something like that, right? Anytime the input happens, then the output. And so you basically got the input and you got the output, and then that's it. In this case, X or Y, then, I would say, I'll just put in action, maybe, is kind of what you're getting. That's typically what you're after. So the key word, though, from this, what we just did with this circuit, we basically, it wasn't if this is closed, it was anytime this is closed. Which also meant anytime it was unclosed, anytime, it wasn't if this is closed, then this goes on. The key word is anytime, because if this opened back up, this immediately went back off. So the logic was always being evaluated. In this case, it was an analog evaluation, but it was always being evaluated electrically. If we were to finish drawing this diagram then, with this in mind, we would say, well, let's start over here, and let's start over here with what we want to control. What should we do? I don't know, let's turn on a light. How about a light? All right, so I'm going to draw a little box here, and let's see. I'm going to call this light. All right, and over here, if I want to control that, I'm going to turn on a switch. If I connect those, that's a circuit, right? I drew my switch a little bit different. This switch here, its action is on off like that. Okay, so that's the first thing. Now let's see, what else you want to do? Let's, what are some of those other things we had? We wanted to, that one's pretty easy. You could put a switch in here, and the logic of this says that anytime that this switch goes true, then this light turns on. I think that's pretty obvious, right? What if you wanted two switches? You guys have this in your house. You have some of the rooms where you can go to one side of the room and turn on the light, and then you can go to the other side of the room and turn off the light or the fan, right? Everybody familiar with, you know, two-way switches?
Yeah.
Okay, so let's say I wanted either one to turn on the fan. What would the circuit look like? Well, it'd be over here on the input side of things. So it'd be somewhere over here. We're going to need to draw another switch. Where would you put the switch? You would put it right here. Right? So you put two switches in parallel with each other. And that would say, if you think of the logic, then back to it always starts with anytime, because anytime these are both open, the light's off. So anytime this X and Y, I guess we should put a little extra thing in here. We should put anytime X and Y are true. And when I say true, I'm really starting to reference the whole Boolean thing. You know, Boolean didn't come around when Boolean was there. The logic of and or and nor logic was around centuries before there was ever a microprocessor, right? And so we always know that things are true or false, on or off. And in the digital world, we finally started to call this 1 or 0, right? Give it a 1. If voltage is high, it's on. If voltage is low, it's off. So, and this whole logic was that Boolean logic. What logic would this be? This would be, would that be and or?
Or?
That's or, isn't it? Yeah, that's or. So where would we put the switch if we wanted to be and?
Behind it or next to it?
Yeah, right next to it. So I don't know if this is gonna work or not. Nope, that didn't work. Yeah, that'll work. Okay, so I'm gonna say instead of that, we're gonna do, let's put one in right here. Oh, you know what? You know what? Let me do a different kind of switch. Let me back this up. Okay. Let me put in, you know what that is?
Normally closed push button.
Correct. So this one is normally closed. These I drew as normally open. And you can do either one. In fact, you guys did, if you remember those, you probably had those little rocker switches that I gave you, and they had a couple little tabs. I don't know if we got this far, but you know, you can buy a little rocker switch. This is a little roller, and inside here, the actual circuit of this here's this one. This one is open, and then this one is closed. And so you can either wire up to it. You can either wire up. These are little wires that you can come up. You can either access the normally open side or the normally closed side. It's two switches in one, right? So not all switches have this capability of having either or, but that's when you had these three terminals. It was just two switches in one is what you had. So back over here, we've got a normally open. Here we've got a normally closed switch. So what would the logic of this say? If we were to write out this sentence of this, we would say anytime, okay, we need some labels here. I can see that. We need to go back and label this. So let's label this switch 1 and switch 2, switch 3, and we'll label that. We already labeled that one light, okay? Light. So now the logic of this would go like this. Anytime, this would be the sentence, the logic sentence that you're essentially solving. Anytime switch 1 or switch 2 is true and switch 3 is not true, then the light turns on, right? So that's the logic that you would have. And you
So
yeah, go ahead.
switch 3 is always there's current always going through switch 3
Until somebody pushes the button and then it's open.
So
It's
it's
just
like
the
a-
exact opposite logic, that's all,
okay.
right? So you can have switches that are normally closed, and when you push the switch, it breaks the circuit instead of
Yeah.
makes the circuit. So it's just the opposite of the logic. Whether the spring is, when the spring is holding it closed or open, and you push it, you either open or close it. So you can make it one of two ways. Make sense?
Yeah, like the ones that you push on or push off switch kind of thing. Except this was always on.
Right. There's a couple different kinds of switches along the way that you deal with. There is momentary switches, and momentary switch, and then there are regular latched switches. So the momentary switch is one that would be true while you're holding it or false while you're holding it.
Yeah.
Right? You're pushing on it, and then when you let go, it switches state. And so there are some switches like that sorry about that, that you would have. Do we have any of those in your world? Well, momentary switch. Yeah, every time you start your car.
When you beep.
Yeah, your horn. Yeah, can you imagine if the horn switch was the switch that was like
Latch.
this one, and you push it, and then you got to push it again to make it go off, right? So
Yeah.
the momentary is like your horn on your car, the starter switch on your car. So we got lots of different kinds of switches that you can put in here. But the bottom line is, think about what I did here. I actually made a circuit. So plus voltage comes over here, gets attached, goes through. Let's say this is the switch that closed. Current flows through here, flows through here, turns on the light, and then, like any good circuit, comes back to ground, right? So I physically made a circuit without a microprocessor, and I made some logic. So this is what you used to do. And okay, now let's add a couple more things to our circuit. Let's say that what were those other logic things we wanted to do? We were doing the other inputs. So we did the sensors or the switches. So let's go think about what would you do if you wanted to time something. Let's say we want to leave this light on for a period of time. And so we had a mechanical timer that we were going to put in there, okay? So let's go back to our ladder logic. And we know that we can have multiple circuits. So let's make another light. Let's make a motor that turns on when the timer times out. We turn the motor on for a certain period of time, and then we turn the motor off, okay? So you always start over here on this side. So let's be consistent with color. So let's have, we'll label this motor 1. Okay, and we better make sure it's attached right there, motor 1. So electrically, we know that if you have a DC motor, and you give it voltage, it's going to turn, right? We did that in class. All right, so we want to put in a timer. So let's draw a box for our timer. So let's just draw, let's put in somewhere over here on the input side of things. On the input side, we're going to have a timer. I'll just label it down here, timer. All right, so what goes on in a timer? What functions do you need to have in a timer? Let's see, you need to have something that tells it to start, right? You need to have a timing mechanism inside, and you need to have an output. So let's say that, oops, let me go back, add that back in. Let's say we have, okay, let's have my box back. There we go. So let's have some connections to this thing. So down in the timer, let's say that this down here, this is the timer section and this is the logic section. Logic, we would like to have some sort of switch. In this case, we'll call it switch 3. Why not? Let's add another switch. Switches are cheap. Let's add another switch. So we put in switch 3. And in this timer, at some point, you need to tell it how much to time. Days, seconds, minutes, right? Whatever. So we need some place in here where we set the time. And so let's just call that area over here, let's just call that PT. And PT stands for, let's see, where can I write this down? PT is preset, because it's preset time. All right, and then let's see, if we want our circuit to work, again, before microprocessors, if we're doing this just with circuitry and with devices that you got laying around, you would say, all right, the output, let's see, do I have a circuit? Let's see if this works. So to start here at the voltage comes through. So the logic is anytime switch 3 is true, then the timer starts. And the timer, the key to the timer though, is we have one more thing over here that we got to draw in. We got to draw in Q, is what we're going to call this, the Q variable. And the Q is just the output. That this Q is the thing that either goes true or false. And so back to our circuit. So we came through here, and the timer, when the switch closed, the timer started counting. The trick to this is this line right here didn't see electricity until the timer was done timing. You triggered, so you add this extra little piece of electrical stuff in here that, yeah, you triggered it with your switch, but then it didn't really go true until a little bit later. Do we have any examples of that in the real world, where you see you hits the button and then something happens with a delay without a microprocessor? Where does that happen? I'm thinking along with you. Something where you hit a button and there's a timer and then it starts.
It wouldn't be a stoplight. I mean, stoplights probably have microprocessors.
Yeah, but you could do this with the stoplight, right? Is there any reason, if you had some mechanical timer, that you couldn't have, a car triggers it with a physical switch under the pavement and a pressure switch or something, and then it physically starts a timer going, and then click, it goes. Yeah, timer. That it could be. What else? What else would have a timer function in it that you press? You do the logic, and then knowing that you're going to have a delay before the other thing comes on.
Toaster.
Oh yeah, toaster, huh?
Yeah.
Now, okay, is your toaster a timing thing, or is that probably has a little heat sensor in it, right? No? What's going on in a toaster? That's pretty much timed based, isn't it?
Yeah, I would think so. Unless it's just like some little spring waiting to.
Yeah, I don't know.
No
I got
idea.
I made toast this morning, and I had a little slider, and I slid it back and forth, and I never really paid attention to, you know, I know that if I don't like the toast on the first time, I slide the slider up a little bit more, and yeah, so we have these things, right? So nothing tricky about it, and you can preset the time with your little slider operation. You probably has, you know, mechanism. So let's go back to our circuit then. So now the Q, after the timer has timed out, then Q after that delay went true, and we now pass current through. Let me draw this just so you got it here. There's a coil. There you go. So now motor turned on, and we got back to the ground. So it works. So we turned on a motor with a timer. No microprocessors. Okay. Well, I just programmed a PLC. If you open ladder logic and the ladder logic program of a PLC, the program, even the fancy new Omron ones that we're going to do, this would be what you have here. This whole thing that we just got through doing, this is an example of the programming language in a programmable logic controller called ladder logic. Why is it called ladder logic? Can anybody guess? Look at the diagram, right? So let's say that you did want to, you're back in 1987. All right, it's 1987, and you have these microprocessors, and you say, hey, let's make something that instead of the actual physical device here, what if we want to do something? What if we decided that this switch 2 was in the wrong spot? Okay, in our pre-microprocessor system, or let's say we want to add one more switch. You know, we want to make a change to anything in this. We want to make a change. What do you got to do to make a change to this system in the real world pre-microcontroller? What tool do you go get out?
Wire cutters?
Yep. Get out your wire cutters, and you get your screwdriver and your wire strippers, and you start rewiring things, right?
Yeah.
So you would say, oh, let's add another switch. Let's add a switch right. Let's add a switch right here. Okay, well, what do you got to do? You got to cut that wire. Like I just did it magically with my Apple Pencil. You got to cut that wire, and then like, all right, let's put in. Ooh, I know. Let's put in some sort of. We could put in a timer right here on this one. We could make it so that this light will stay on, but if somebody left the room and left it on, after 2 hours, we'll turn this light off and save power, right? Why not? So to do that in the real world, you would have had all this wiring to do, right? To make the timer in here. And so microprocessors come out, and the programmers say, hey, wouldn't it be cool if we could, instead of getting out the wire cutters and snipping that wire and snipping that wire and wiring, you know, soldering this or crimping this in place, wouldn't it be cool if we could literally do what Nick is doing right now? I'm going to do this. And I don't want that anymore. I'm going to take it out. There, it's out. And so they said, yeah, let's make a language that does that. So if you were to make a language and you're going to automate something, you're going to make the first PLC controller and you think about who's going to be programming this in the real world, all these people that are out, the people that are out making these machines or trying to automate these machines, do they know how to program in Fortran or C, or they don't know any logic language. They don't know how to program yet. They've never even heard of programming. Programming by lines of code isn't necessarily something that everybody knows how to do. So if you're designing a product, you would design a product so that your customers could use it. Well, your customers know how to do this. They know how to wire things. So if you're designing a language and you want to put it on a screen, you design a language that looks just like they're used to dealing with in circuit, except for the one thing we can do is we can do this. We can add a switch just by clicking on it with a computer. And so you now have a mechanism, a language that you can recreate. And if you can recreate this just like I did in a computer, and you can go click on, you have in today's world, in the programming environment, you would have, if you pulled this screen up, why isn't my, there we go. Let's say you have your programming screen, up along the top here is a whole bunch of different things. Here is that one, here, that's the normally open switch. Here's the normally closed switch. Here's the timer. Here's the counter. And in today's world, what would you do? You'd say, oh, I want that one, right? Oh, and we need a couple more things to program the PLC. If you were designing the program environment, you would say, oh, wait, we got all the input stuff over here. We better have, so these are the inputs. We better have some outputs, right? So now I'm designing a language. And so what do we need here for outputs? We needed a light, and we need a light. Hold on, I ran out of room on my words. Light. And what else do we need? We needed a motor. Okay, so now here's how we do it. We say, let's have a normally closed switch, and you click on it. And voila, what happens is it shows up down here. And there it is. And this is exactly what would happen if you were to run the Omron stuff. It pops up in there. You can imagine this. I was like, okay, now let's go up and let's click on a motor. And when you click on the motor, whoa, what shows up? Motor. And it shows up like that. Now, probably at some point, then you say, oh, there they are. How do I make them work? Oh, I need to connect them, right? So you come back over here and you grab your pencil and you physically connect them. There you go. You just programmed a PLC. You just programmed a circuit. And then the trick is, with the trick is that the PLC evaluates the logic every, let's say 1 millisecond or so. Okay. So what really happens now is in the circuit is we still have the plus and the minus, and this is on a computer screen, but when you design this programming environment for your user, you being the maker of the PLC, when you designed this programming environment, the user knew exactly what that meant. He knew exactly what these things meant because they'd been using them for years. And so you drop this in on them, and as a language, there's not a language to learn. There's not a new, they don't need to take a college class to figure out how to use this. They need a little bit of training, how to click things. But what shows up on their screen is exactly the same thing that they've been using. And so all the users of the machines then can use this language almost inherently. And so that was, let's see, that was 1989, and we're in 2020, and very little has changed. And the reason that very little has changed is because if I asked you to go make a flashlight today, you would still go get physical components. You would still go get a power supply, you'd get a physical switch, and you'd get a physical light bulb, and you'd run wires between them. So the thing about wiring things up actually hasn't changed. And so this language still makes sense once you understand that it's modeling a bunch of circuits. And the tricky part with ladder logic, if you can imagine, is what happens when you start to get 1 circuit, 2 circuits, 3, 4, when you start to get bigger and bigger machines, and now you have 426 circuits to keep track of. And the only thing you have is they're all active all the time. That gets a little overwhelming. And so at some point, then you start to say, you know what, this is overwhelming. I'd rather have if statements. I'd rather have subroutines. At some point, moving to a text-based language.
So would that be kind of like in our cars, like the ECM?
It would. Yeah, but the ladder logic is a form of programming. So you could have dropped a ladder logic controller into your car and programmed all the things just like what you want. In fact, I was just doing a race pack system for my buddy on his race car, and I pulled up the race pack system, and it looked like this. They had it programmed. It was kind of a sort of a ladder logic type of thing. They don't try and force non-programmers to program in a text-based language. You guys will all learn text-based language. You'll learn MATLAB. You'll learn maybe C. You'll learn Python. You're going to learn these text-based languages. But not everybody, a very small percent of the population knows how to. And that, when you do that, go ask somebody, hey, do you know how to code? Do you know how to code? No. But anybody could understand circuits and making circuits that match and using logic. Lots of people get that. So that's not surprising then that here we are in 2020 and we have a controller that is really good with simple Boolean logic and a simple representation of it on a screen, and you bring it up in the computer and it makes it super easy to change out. Oh, I want to add something right in here. No problem. Let's add, oh, I know, what's the one thing we haven't done yet? We did switches, right? We did outputs, inputs, we did a timer. What's the one thing we haven't done yet?
Power.
No, okay, good point. Let me just make sure we see this. So so you can see this, let me just draw this in. This is always this is somewhat unsaid, okay? I'm gonna draw that around there. Okay, so that's the thing with ladder logic is they dropped the red line part of things. They dropped this from the screen. And so they only show you, the stuff that's in the box. And they dropped this. And I drew it from the very beginning so you'd understand that we're recreating circuits. Okay, so we did timers. Oh, we did switches, outputs. We got one more.
Counters.
Counters, right. So we had the counter. Okay, so why don't we make a counter? Oops. I guess I could have left it that color, but let's make a counter. Okay, so a counter and timers are both, now we've moved into the PLC library, those are both function blocks. So we want to go get a counter function block. Now, counters have a couple different things. You can either count up or you can count down, right? And in this case, anytime this switch opens and the counter has counted, then the machine shut off or not run anymore. We need one more thing in the counter. We need something down here, and we need something called PV, and PV equals the preset value. Okay, and so if this was a count up timer, then you would set the preset value to however many counts, and if you set that at 10, and once we're into the computer, once we're out of the realm of the electrical circuits, we're done now with the wiring part of things. We're doing all our wiring in the virtual environment here, right? Where we can change things around. We can scratch out that motor. We can say, you know what? I don't want a motor there. I want an actuator. It was just literally that easy, right? A couple clicks and we put it in an actuator instead of a motor. So in the counter world, we need a preset value of 10. And then what happens was this would literally, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then boom, Q goes true and the actuator goes. Okay, easy to represent. Ladder logic is really good at this kind of stuff. And you didn't have to learn any text-based languages. And so since circuits are still in existence and you still hook them up, you still, when you're doing simple systems that are just on-off control, that take into a number of factors. Let's say you wanted to automate something at home and you didn't know code. You could go down, buy one of these little boxes, these little PLC boxes, and you could probably do this language without having to learn coding. And if you go out to the manufacturing floor, that's where we still are. Luis, yeah.
So when you say PLC boxes, like, is it like that one machine that we had in the middle of the class that had like a little monitor thing?
Exactly. And that little PLC box that we had in there, it was a well, after we're done here, go Google PLC and you'll see it's literally a square box, and it had a bunch of places that wires come into it, and you attached it, and then you had a the actual PLC boxes that we have physically look like this, right? They're boxes. Somewhere into them comes in volts DC power, and then there was physically a row of places where you would bring in bring wires. So you'd bring in wires here from different devices, making circuits, and then on the bottom of it you had, oops, I should change color. You had, and literally you had inputs and you had where you wired your outputs. And these are screws here. And so you had wires coming out and going to motors. So you had a box. It also had one other special feature, and it had over here on the side, oops, it had a programming port. And to buy one of these, you pay, I bet you could get a box like this for about $200 if you bought a non-brand name. If you bought the one that's in class, you probably pay $1,000. What do you get for your $800? You get a whole bunch of support. You probably get a better box. You probably get people that can come out and help you make it work if you can't figure it out. Instead of just the $200 one, you probably are on your own to figure it out. The $1,000 one, they have people that are ready to come help you. So you might, if you're just automating your blinds in your house to go on when the sun comes up, you have a sensor that when the sun hits it, the sun hits the thing, the input goes on, and anytime you have that Boolean language, anytime the sun hits the sensor, the motor comes on and opens the blinds for you. The reason I bring that up, that's what my wife wants me to make. So I think I might be making one of those here pretty soon. She says, I'm tired of opening the blinds. And my thought is it really that hard? But she wants it automated, and she looks at me and says, aren't you the guy that's not supposed to know how to automate things? Like, yeah, that's me. So I could probably buy the $200 one just fine. I don't really need the guy. I probably am the guy that might come help you. So depending on, where you are, where your manufacturing capabilities are, you may want a lot of help, you may want a little, so you buy a different, but basically you all get this same box, a PLC box with inputs and outputs, and you're going to connect it to, over here, you're going to connect it to your PC to program it. Now, the one thing extra we had in class, we also had it's called they call it a HMI, stands for human. Now that we can't call them man. They used to, for a while, they were operator input panels. They were machine interfaces. Now they're human machine interface. That's what an HMI is. So, and on this little HMI thing, you had a little screen on it, and then you could put all sorts of little things on it, and then you physically ran that into another port. Let's see. You ran that into another programming port and connected it. These days, you would connect it probably on the network. It would have a small little network that's running on it. And so, yeah, that was what's in the middle of the room. And here is that's where you're running the ladder logic. Ladder logic programming is in here.
So the HMI was like where you probably select what you want.
Yeah, this was a touch screen. Right? So, yeah. Yep. All right, well, so let's see, our counter circuit here, I'm backing up a page. So we did our counters, we did timers, we did inputs, we did outputs. Do you think if I drop this in front of you with this amount of knowledge that you could probably figure out how to run the program and figure out how to turn on and off an actuator with a switch? I think so, right? I think you get it. So there's really not that much more to PLCs. I mean, we make a big deal about it, and in the PLC class, what we would do is you'd power up the program, and you would start to actually, all right, you think about over here, what's the output? How many outputs do you have in your machine? Well, you'd start counting them, and you'd say, all right, in your machine, let's add another one. So you'd start listing, all right, what outputs do you have? You'd say, all right, we have motor one, and that controls that spins the rods. Okay, what else do we have? Oh, we have actuator one. We have a linear actuator, and what does that does? That loads the utensils. This is what you would do if you were to start programming. You'd start listing, all right, what other actuators? And so actuator 2, let's see, what else do we have? Actuator 2, physically, what else you got to do with that? You need to load the utensils. Oh, you need to pushes into the box. All right. So once you start to define what outputs you have for your machine, now you can kind of start to see what your ladder logic program would look like. You'd have this one with a bunch of logic attached to it. You'd have this one with a bunch of logic attached to it, and this one. So you would actually have a word problem that you would start to write. All right, let me, on actuator 2, what's the logic in words that makes that work? And you would start out saying, all right, well, let's just see that. So anytime, okay, so what happens? Anytime timer 3 is true, and timer 3 happens to be the one that allowed the motor to spin for a certain amount of time, and the machine is on, you haven't turned the machine is off, so the machine on is true, then turn on actuator 2. Okay, if you could say this words, if you can actually say it like that as a sentence and say all the logic, essentially what you've done is you said, here's the inputs that you need to program. You need to represent this, and here's the outputs. And you'd go represent that in your ladder logic program, and that part would be programmed. That's all, and then you'd be done. And if you wanted to change, ooh, let's go back and let's change this timer. It's not quite right. Oh, well, that's easy. If the timer's not quite right, let's go back into the timer, and on this preset time, let's set PT was 3.6 seconds. Let's change it to 3.9 seconds. We need a little bit more time. Okay, so you put in 3.9 seconds, goes in, and now you've changed the time. Versus what you would have had to do before, which is go out and mess with the mechanism and trying to get it right. Now you can just do it in the programming language. So in a way, it's kind of a language. You have variables that you can use. You have math that you can do. There's a capability to do math. You have, what else do you have that you need? I'm running out. Anyway, so that's what you would do. That's the essence of programming your machine using ladder logic. Now we could we could change it into a text-based language and have you use in today's world. If you're a coder and you know you've learned code, you might go grab instead of buying that, you might go buy microcontroller, right? If you could go down and buy yourself a little board with some circuits on it, right? And it has a little connector over here that you plug into and a little connector over here that you plug into, and it's got a little USB port, right? Port on it. And this thing runs, it runs what? It runs text-based code. And how much does this little Arduino or PIC or whatever controller level controller you wanted to buy, how much does this thing cost? If you want to, if you know how to code and you want to put up with a little bit less, these are not these connectors were not necessarily very industrial. Right? Not industrial connectors. They're not necessarily industrial, but how much would you pay for a Arduino these days?
Under 100?
Keep going. How far under? Who's bought an Arduino lately?
Like
30 to
60
80?
bucks?
It's like $70, yeah.
What? 70?
I bought it for like $5.
I mean, yeah, you can get,
Yeah, I think the Uno was, in my other class, people were buying for like $12. All right, 12 to 50 bucks. Something like that, depending on where you bought it and who you bought it from and the distribution method and all that kind of stuff, right? So the point it is not industrial. It's up to you. This is an open, this is open circuits, open circuitry. It's not something you need to put a box. If you're going to do anything and productize this, if you want to productize this, you better put a box around it. That's no biggie, right? But if you're only building one, maybe you don't care. If you're building it for yourself, you might not care, but I'm kind of trying to get you ready for, all right, you now work for a manufacturer who's making things. Are you going to put this in there and use text-based code, or are you going to go put in an industrial box that's going to have support other than you? It's not attached. You don't need to essentially tell them your phone number once you leave this behind. So these PLCs, the Arduino, they're not industrial. You need a box around it, but they're only $12. You know, they're $12 to $50. You can. This is the kind of thing that you can put in a machine, but this is designed for people who know how to code. The PLC is designed to get a machine working. It has a box around it. It's industrial. It's going to work for a long time, and it's got a very simple language that lots of people can pick up. That's not really a language. So I think that's it. I think that's end of PLCs. It's, to me, I introduced this a little bit different because I wanted you to understand the context of why they're still around. We have manufacturers and previous students, they go out to work and then they come back and they sit on the advisory board for the college. And it's, let's see, how many years? Let's see, it's been, let's see, 19, so we're in 2020. So we're only 30 years into this, roughly. 30 years later, this thing was invented 30 years ago, and they were working 30 years ago. And guess what? There are still ones in industry that are 30 years old that are still working just fine. And it's still current. amazingly enough. And the reason it's current is because this language makes sense to people that don't know how to code. And so what happens is if you're the manager of a company and you got a machine coming in and the machine manufacturer, you as the person that's going to receive and buy the machine, you want your people out on the factory floor to be able to run this thing. Guess what they know how to do? They know how to do this. And so there's still a huge draw that if I'm going to have a machine be built for me and come into my factory, I want my people to be able to run it and program it and make changes to it. Well, you know what? They can do ladder logic. All right? Make sure that you put a ladder logic controller on my machine. Is it the best machine? No, not one bit. Is it the best controller? No. Is it a little slow? Yeah, but it's fast enough. So we're still we are actually transitioning away from it slowly as more of you get out into the factories and can receive the equipment and work on it. The more people there are that know how to code, the more when something like this comes in, everybody's happy with it. Oh, look, it's an Arduino. No problem. Here, we got 5 people around here that change that program. Good. Now when something goes wrong, you're not just sitting there looking around the room going, hey, who knows anybody here know Python? I don't know Python. I know ladder logic. I know circuits. Oh, now more and more it's like, oh yeah, he knows Python. He knows Python. We all, it's more and more common. And so things will change over. And you want them to change over because these microprocessors can do a lot more intricate operations than just turning things on and off and the Boolean logic that you get with PLCs. So that's my lecture for today.